Okay, welcome to EE380, the Stanford EE Computer Systems Colloquium for March 2nd, 2022. The speaker today is Dave Ditzel from Esperanto Technologies, and he's going to tell us about a new machine that they have in progress with thousands of cores and performance that's amazing. I think it should be very interesting. In any case, Dave, I'm not going to tell anybody about you, though I will say that you started out at Bell Labs, made a number of machines there, went on to Berkeley, made stuff there, went to Sun, made stuff there, went to, well, on and on and on. Someone mentioned that they thought that you just seem to be making machines on a regular basis, and it's going to be boring to hear about your new stuff. I don't think so.
Yeah, I think it's the sixth talk I've given for the EE380 series.
That's right.
Or whatever incarnation it's been. I went back and counted just a little bit. So 35 years of presenting the EE380.
I think it's marvelous. The fact is, you've never been to a bad talk, so I'm looking forward to this. So
okay,
you're on.
Great. Well, thanks everybody. I see a lot of familiar names here. We're going to have some fun today, I hope, and that we'll be able to go into a little bit more depth than I can typically do into a squeezed conference presentation here. And I'm excited to tell you all about Esperanto's first main chip. There's many more to come. We're going to talk more about hardware today than software. Accelerating AI is just a giant topic here. And, you know, for the software, so we can just get some context, I'm going to talk more about accelerating recommendation, because there's lots of kinds of things to accelerate machine learning. And we're going to do that in a kind of interesting way. Rather than kind of a special purpose chip that's oriented exactly towards machine learning, we're going to do it by accelerating programs with over 1,000 RISC-V processors on a chip, with some special enhanced hardware and architecture. So we'll go through that today, and we'll take some questions at the end here. So one of the interesting things is, of all the chips being built today, we think we've got the world's highest performance RISC-V chip. In the sense of putting the most RISC-V instructions per second on a single processor here. We have over 1,000 RISC-V processors on a single 7-nanometer chip. And for those of you who follow processors, think about how many processor cores you have in your notebook computer or pad, or even in a server. And it's a number a lot smaller than 1,000, typically maybe less than 30 or something than that today would be typical. Of those, we have actually 3 different processor types. We have 1,088, and you'll see why that number comes about later, of our energy efficient, we call our ET Minion processors. Those are full 64-bit RISC-V processor cores. They're fairly simple in-order cores because we're going for energy efficiency with these cores. And each of those has its own dedicated vector tensor unit. And I'll go through a lot of detail on those cores today. In addition to those energy efficient cores, there are times where we want to operate standalone and you'd like a fairly high performance single thread execution. And so we have a processor we've designed at Esperanto called our Maxion processor. And those are, again, full 64-bit RISC-V cores, but using an out of order pipeline. I've only got one slide on that today, but we'll go over it a little bit. And then there's one other core we have, which is a RISC-V processor we use as a service processor, which is a little bit different. But in addition to cores, you have to keep the cores fed. And so given how fast these cores are, you want a lot of on-chip bandwidth. We have over 160 million bytes of on-chip SRAM. We'll show you how we've architected that. This is a full system on chip as well. And we have interfaces for large external memory. Again, because we're very power conscious, we've used low power DDR4X DRAM. We also have interfaces for flash, because for certain kinds of machine learning, storing stuff in flash turns out to be very helpful. We typically operate in a mode where we're an accelerator to a host in a data center. and to talk to that host CPU, whether it be it usually Intel or AMD. We talk to it over 8 lanes of PCIe Gen 4. And when we put all this on a chip, it allows a single chip to generate peak rates of 100 to 200 teraops per second. Now, again, the trick is not so much to get peak rates, which is what everybody likes to quote, but it's how to get high sustainable rates of computation. And that's what a lot of this talk will be about today. Now, you may have seen people put a lot of cores on a chip, but typically when people try and cram a lot of cores on a chip, that chip might be 2 or 3 or even 400 watts. I think what's really interesting here is that we come from a background of low power techniques, and we're able to do this, particularly for running machine learning recommendation, where we expect to be able to operate the chip using typically under 20 watts of power. So that's one of the keys to what we're doing here. Now, with 1,000 RISC-V processors on a chip, you could do a lot of different things. Almost any workload that's parallelizable, you could think about distributing amongst these RISC-V cores. But that, again, is a giant topic to talk about what we could do here. So today, I'm really going to focus on machine learning recommendation, and more particularly inference with recommendation there. And part of the reason we focused on that is it's one of the most important problems for a lot of hyperscale data center customers here, in addition to being a fairly hard problem in its own right. So let's talk about how we deal with that. So first of all, what's challenging about recommendation? How is it maybe different than other kinds of workloads? And why go after data centers? Well, data centers is where people buy lots of chips. And as a startup company, you want to find customers who want to buy lots of chips at once. And rather than selling to 10,000 customers, each of whom buy 3 chips, we thought it'd be a lot easier to start off with targeting just a small number of data center customers, each of whom could buy a large number of chips. Now, a lot of these servers that are running the ML workloads that you all use today, and recommendation, just so you know, is that when you're in a web browser and you're visiting somebody's website, you'll see advertising come up. And recommendation is where they may recommend you want to buy bicycles or red shoes or a certain shirt. They're basing that across your personal history, and they will try and recommend particular advertising to you. So this is how they make a lot of money. Now, a lot of this workload today is run on just standard x86 processors. And those servers tend to have an empty slot a lot of the time. In our case, there was a particular customer, they had 1 empty slot available with each x86 CPU. But in order to serve as an accelerator chip, we had to meet a couple key requirements. First of all, you need to be faster than the host CPU that they already have, right? If you want to plug in an accelerator to that existing system. So that meant we needed to deliver on the order of 100 teraops to 1,000 teraops peak rates in order to provide sufficiently better performance than the x86 CPU already had. They also had a limited power budget. In this particular case, it was less than about 120 watts. There are other PCIe cards and other systems that have 75 watts. And in particular, when you have thousands of these servers and data centers, I think one of the more interesting lessons is that they really wanted these to be air-cooled. And there's you'll see a little kind of a footnote here to a reference for a paper. This is to a Google paper that talks about how they had mistakenly tried to do water cooling in their inference and really regretted it later. And so those references will all be available at the end of the presentation. We can go over those. I'll try and reference those. And again, in looking for data types, people have done all kinds of clever things, 5-bit integers or specialized floating point format. But really, we had a lot of feedback when we interviewed our potential customers. They said, look, just focus on 3 data types: int8, which is really great, FP16, and FP32. If you invent some other specialized data type, realize you are not the only company who's going to be selling chips to us to accelerate machine learning. This is going to be a heterogeneous environment. We have to live with Intel, AMD, NVIDIA, various other people. We're not going to be transcoding data between one or the other just because you have some fancy data type. They said, look, spend all your effort there. Don't waste any logic gates on doing anything else. because you'll just be wasting power for something we're not likely to use. And that's pretty consistent. There's a second paper I reference here from Facebook, which says pretty much the same thing. How much memory capacity? The customer said, look, you need to hold on the accelerator card on the order of 100 gigabytes. If you do that for most of the inference work we do, you can hold what we need on the accelerator card, at least the most important part for holding embeddings, weights, and activations. And that's good, but you can't fit 100 gigabytes on a chip per se. And so you can, while you put that on the board, it's still important to have memory on die, because that can still be very frequently used and have much higher bandwidth. And they recommended about 100 megabytes. And in fact, at the beginning, when we went out with the proposal from Esperanto, we were proposing, I think GraphCore had 256 megabytes. We thought, oh, that's a good idea. And we got pretty consistent advice saying, hey, don't waste more than about 100 megabytes with on-die memory. If it doesn't fit in 100, it's not going to fit in 256. So that's why we went with just a little over 100 megabytes. It was very important to handle both dense and sparse workloads. So dense workloads, you might imagine all the data fits in a little cache and you can compute all the time. But a lot of these things are fetching data that's kind of random in memory. And embedding in particular is a lookup of, a sparse matrix by dense matrix multiplication here. So you have to be able to randomly access this 100 gigabytes and do pretty well with that. It's very easy to build very high performance machine learning and have very impressive, teraops per watt if you can keep everything on die. But again, for the applications we were going after, these large commercial applications, they said, look, that just isn't possible. You've got to reference 100 gigabyte. So how do you deal with these sparse workloads? And in particular, they were really looking for programmability. There was a lot of view that a lot of the hardware they had seen was what they tended to call overly specialized hardware. Okay, that's really great. You build hardware that does the inner loop of ResNet 50, but nobody really runs ResNet 50 as an actual workload. The workloads are changing all the time, and they were really looking for more programmability. So if there's anything to come out of this talk that I'd like you to think about, it's can you compete in doing machine learning acceleration with a general purpose processor? Or do you really need specialized hardware to do it? And one of the challenges Esperanto took on is to prove that you could, in fact, use general purpose hardware if you had the right kind of general purpose hardware and you built it to be very energy efficient. So we'll visit that at the end. So let me see if I can contrast Esperanto's approach versus, well, there's so many different AI accelerator chips. So let me overgeneralize a little bit here to the ones that tend to be closer to our space. But we see a lot of approaches that build what I call the one giant hot chip, right? And on that, they'll tend to put a lot of array multipliers, whether they're systolic array multipliers or some other kind. That tends to be very effective. And then they'll put maybe 10 to 20 more general purpose CPU cores there, and then connect it up over a very high speed interface, maybe something like HBI memory, because you have a limited number of pins to talk to the DRAM. And so you use all your power budget there, and you'll see a lot of 300 or 400 watt chips or things that are even hotter than that. So our approach was a little bit different. Rather than building the largest chip, we build a moderate sized chip and use multiple of those chips that still try to fit within the same power budget. So why do we do that? Well, if you have just one chip with one package, you have a limited number of IO pins, you have a limited amount of memory and a limited amount of memory bandwidth. So if you use multiple chips, your performance, the number of pins you have, the amount of memory, and the bandwidth will all scale up with the number of chips. If you use array multipliers, yeah, that can give you a great ResNet 50 score, but it's not really very good with large sparse memory. And you'll find as you go through multiple layers that the matrix stops being a nice square shape, which fits on an array multiplier, but maybe your data will get tall and thin, and it doesn't fit so well on the array multiplier again. By contrast, by using thousands of general purpose RISC-V cores with tensor accelerators, we ended up with a far more programmable solution. And to deal with the large memory latency when going to that 100 gigabytes, we used a similar technique to what a lot of the GPUs use. Thousands of threads help with that large sparse memory latency. If you have a case where you only have 10 to 20 general purpose cores, that really limits the amount of total parallelism you have. So anytime your problem doesn't fit perfectly onto that array multiplier, you can only fall back to, say, a parallelism of 10 cores in parallel. Whereas with the Esperanto approach, we have the full parallelism of thousands of cores always available. So long as your program is parallelizable, and most AI programs are, you can take advantage of that full parallelism. And then, in terms of physical implementation and circuit techniques, most everybody else tended to operate their chips at standard voltages. And as I'll show you coming up, we believe that was not the most energy efficient place to operate. Instead, what we do at Esperanto is we operate the power hungry portions of the chip at very low relative voltages. And that's because when you operate transistors at much lower voltages, they actually are more energy efficient. Think of my analogy I often use is a car going down the highway. Yeah, you can have a car that goes 100 miles per hour, but you're probably using your gasoline more efficiently if you drive at 30 miles per hour. Same kind of thing happens with transistors. Most of the semiconductor fabs, put a nominal standard voltage for a chip that gives the best performance, but that's not always the most energy efficient place. Well, why doesn't everybody operate at a lower voltage then? Well, it turns out it's not so easy. While lower voltage operation reduces power, you've got to have specialized circuit techniques. And we actually changed the actual architecture of the CPU so that it would better match what happens at low voltage. In fact, a number of the accelerators out there use approaches that just aren't amenable to low power. For example, they put fairly large caches or memory at the first level, and you just can't scale those down in voltage very well. So given this particular approach, we were going after a certain set of customers that said, look, how much performance can you put on a single accelerator card with a 120 watt limit? And I'm going to use that as an example today to show you how our particular solution approaches that particular problem, although it can be used for other problems as well. So if we had a physical limitation with one card, we can only mount 6 chips and all the DRAM and power supplies and everything else on a card. So we start off with that constraint. So therefore, if you take your 120 watts available, divide by 6, it means each chip complex has to take less than 20 watts. So for purposes of this example, we assume that about half of the 20 watt power we'd have available would be available for 1,000 cores. We don't get all that 20 watts for 1,000 cores. We only got half of that. So that only leaves you about 10 milliwatts per core. So let's compare that and see how much of a challenge this kind of a problem is. Now, here's what we typically call the iron rule of power here. Your power is CV squared F plus leakage here. And the C there is the dynamic switching capacitance. It's the capacitance that inherently a wire has, or it's the capacitance you get by touching, typically most of the capacitance is the gate of a transistor, although there's a little bit from touching the drain or source of a transistor as well. The voltage, that's just the normal supply voltage, but that's times the voltage squared and times, say, the frequency in megahertz plus leakage. And the leakage, it will depend a little on how you want to operate, but typically on a modern processor, that will be maybe 30 to 40% most of the time here. So let's take a look at how hard a problem this is by looking at, say, a generic x86 server CPU you might be familiar with. So we just went to a typical part and looked at the data sheet, and that was 165 watts, and they were able to support 24 x86 cores. So what that means is you have about 7 watts per core, and if you're running at 3 gigahertz, and voltage, we guess they vary a little bit, about 0.85 volts, and you can just back engineer and say, well, that means the switching capacitance would be 2.2 nanofarads. So what was our challenge? Well, we needed to operate with 10 milliwatts per core. We wanted to run at about 1 gigahertz. We can improve energy efficiency by operating at roughly half of that voltage. And what that meant is our switching capacitance could only be 0.04 nanofarads per core. So that meant we had, in order to hit our goals here to use a general purpose processor, we needed a solution that could be 700 times better than the traditional x86 CPU you might be familiar with. Now, by operating at a lower frequency, the power consumed is linear with frequency, so we could pick up a factor of 3 there. We pick up a factor of 4 by operating at half the voltage, but power is related to the voltage square. But what that meant is that the bulk of the problem of how to fit into the power envelope had to come from reducing the dynamic switching capacitance by almost a factor of 60. Okay? So reducing the frequency was pretty easy. Reducing the voltage, that's a lot more work because you have to use specialized design techniques, and particularly how you deal with both the circuits that burn power and your storage. If you want SRAMs that operate at this low voltage, those are a very special design technique. And the hardest part here, again, was reducing the dynamic switching capacitance. And that really has to do with getting just a simple design. Now let's go talk about energy efficiency for a second here. So we've got this 120 watt problem here. What could we do? So on the y-axis here, I've got the kind of the energy efficiency in terms of inferences per second per watt. And if we simply took our RISC-V 1000 CPUs and we stuck our simplified design and ran it, say the typically way a graphics vendor might do, which is you over voltage a little bit. If we ran them at 0.9 volts in 7 nanometer, the chip that I'm going to talk to you about today would have taken about 275 watts. So clearly over the power budget. If we reduce the voltage to the nominal voltage in 7 nanometer, 0.75 watts, you can see it still doesn't fit. Not one single chip is too much. We can start reducing the voltage until we just barely fit. And that would have been about 0.65 volts. And you can see we're operating a little more energy efficient there. But if you operate at the most energy efficient point for 7 nanometer transistors from TSMC, you get your peak energy efficiency when operating between 300 and maybe 350 millivolts. And that entire chip with 1,000 processors would then only take about 8.5 watts. So that, when you multiply by 6, would in fact have fit within the power budget. And in fact, that would have been 20 times more energy efficient by operating at that low voltage point rather than the high voltage point for the machine learning recommendation benchmark that we're using. Now, notice also that it's 2.5 times more performance by using those 6 chips rather than using one very hot chip. And so that sounds pretty good. However, we're not using up the full 120 watt limit. And so for the server power guys, they say, look, don't exceed this number, but certainly go ahead and use up the full power budget. And so if we use 20 watts per chip, we'd end up actually having 4 times more performance than the single chip performance would have been, and been still pretty good energy efficiency here. So this is why for Esperanto, we kind of targeted our sweet spot to be around 0.4 volts. And again, our chip is capable of operating at a variety of operating points, anywhere we believe will be robust all the way down to about 0.3 volts, but you might want to operate as much as maybe a 0.5 volts. But again, you're going down the energy efficiency point. There are some customers that really care about energy efficiency. As I said, the primary customer we're going after is the one that simply wants the most inferences per second that fit in that power limit of 120 watts. But there'll be other customers simply say, hey, I don't care what the power is, put on the biggest heat sink, run it up at 300 watts. And so we could choose to do that as well with our part. So how do we build the simplest possible RISC-V to get that switching capacitance down? So that's what we call our ET Minion part. It's a custom 64-bit RISC-V processor. Again, in order pipelines tend to be more energy efficient. But to run with a decent speed at low voltage, we had to work very hard to reduce the number of gates per clock. So we could still get to roughly that gigahertz level at roughly that 0.4 volt of operation. So we did a lot of cross optimization across the design domains between the architecture and circuits and physical design in order to enable this low voltage operation. The CPU implements the full RISC-V integer 64-bit instruction set, including compressed instructions. We have 2 hardware threads of execution. And one of the tricks we've done is we've made our level 1 data cache be able to operate as a scratch pad as well as a data cache. And I'll explain how we utilize that in the future. You can see on the right-hand side here, roughly to scale, how much area each of the particular units take. And again, the common wisdom is, oh, if you used a general purpose instruction set, that would take too much area. You couldn't use that. But what you see is in yellow, where the integer pipeline is, that's really not a very large part of the total area of one individual processor. Most of the area is taken up by the vector and tensor unit. And in fact, the hardest thing in that vector tensor unit are the 32-bit and 16-bit floating point multiply and accumulates. You can see in purple here, there's a unit here called the TEMA. That's the tensor integer multiply and accumulate. And again, integer is much simpler to do. You'll see a lot of acceleration chips that just do integer only because floating point is fairly hard here. And on the VPU register file, we support both threads. Something that's a little bit unusual, one of the extensions we did is we actually do support certain transcendental instructions because that was important for machine learning. So we can do vector transcendentals as well. The floating point operates 5 12 bits wide for the integer side, but a little bit unusual is we operate only 256 bits wide for the floating point. And that's because the customer directly requested kind of a ratio of float to int here. And so that ended up with a slightly unusual design here where you have a lot more processing of int. We can do 128 8-bit integer operations per cycle in the vector unit. And those 8-bit ops accumulate to 32-bit integers. For floating point, we operate 256 bits wide per cycle, and you can use either 32-bit single precision or 16-bit half precision operations. You get twice as many half precision operations per cycle, and then you'll be accumulating those for the half precision. You can accumulate either into half precision or into 32-bit single precision per cycle. One of the things that's a little bit different in the extension we've done as well is we've added multi-cycle tensor instructions. So a tensor is when you're multiplying, say, a matrix times another matrix here, and that occurs very frequently in machine learning. So what we can do is operate at the full width of 512 bits, and we can run for up to 512 cycles with one of these tensor instructions. So you might do as many as 32,000 arithmetic operations with one single tensor instruction. Well, why did we do that? Well, it reduces the instruction fetch bandwidth tremendously, and that also helps reduce power. So when you think of multiplying, two matrices by each other, rather than it being in a general purpose program loop that might take a lot of power fetching instructions, running the integer pipeline, we have a very tiny finite state machine that operates the tensor, and we actually put the RISC-V integer pipeline to sleep during tensor operations. And what you'll see when you're running very high performance machine learning workloads, you might be spending 95% of your time in tensor instructions. So again, we reduce the overhead or the cost for using general purpose programming to a negligible amount. So we can provide a very nice programming environment, but we get the kind of efficiencies you would get by a very highly optimized hardwired vector unit, because that's where you're spending almost all your time. We can operate our minion anywhere from around 300 megahertz to perhaps up to 2 gigahertz. And so each individual minion CPU can deliver a peak performance of 128 gigaops per gigahertz. Now, the way we've optimized the design is with a core that's really designed for parallel programming. And so what we realize is in the physical design limitation in 7 nanometer, you can only go a certain distance in your clock cycle. And so we found that we could pack about 8 CPUs together in this proximity. And so we called that a computing neighborhood. And we're able to capitalize on that physical proximity for running parallel code. So for example, when you're running code on 1,000 processors, you'll tend to find that they're almost always running the same code. Notice you have a highly parallel problem, you're multiplying giant matrices, you give each processor a piece of that matrix to go off and work on, right? So rather than having many separate instruction caches that each had redundant code in them, we, in groups of 8, have a common shared instruction cache. So that tremendously increased the capacity we could have in the instruction cache. And because we have tensor instructions that are used very frequently, the fetch bandwidth is actually not very high. So we can share that one instruction cache amongst 8 minions and not have any large performance hit. We do a similar trick with the on the data cache side. What you'll tend to find is a lot of the time the processors are all loading something from the same address, from the L2 cache into the L1 cache. And that's a very power intensive operation. So if you were to do 8 individual loads, one for each RISC-V minion, you'd have 8 times that amount of power. But with the feature we call a cooperative load, when all of the loads are there pending, when the first processor goes out and fetches it, the other 7 processors are waiting, and they simply capture the data that's come back off the L2 bus back to this group of 8 CPUs in a neighborhood. And that was just a dramatic savings in power. You know, compared to not having that type of instruction. So that's an example where you can't just go and pick an off-the-shelf RISC-V processor and put it down and expect to get the levels of energy efficiency we have here. Sorry. Okay. So cooperative loads were very helpful. And there are a number of kinds of instructions we do to make cooperation more efficient here. We have instructions for fast synchronization. We have instructions to send to a neighbor, receive from neighbor, and I'll go through some of those extensions a little bit later in the talk. Okay. How do we then group these? So now we had a group of 8 in the prior slide. What we do is we take 4 of those 8 core neighborhoods and we pack them into what we call a minion shire. We wanted a little grouping, what's larger than a neighborhood but smaller than a city, and we tried various groupings here. So a shire, we had a Lord of the Rings fan. A shire is what we ended up with here. And so we built groups of 32 CPUs together. Now, with a group of 32, we put a much larger amount of memory. We put 4 megabytes of memory together with 4 banks interconnected with a 4x4 crossbar. And that will let us load enough data that we can keep these CPUs busy crunching on that particular data and keep them fed. So again, they can get higher sustained rates of performance, and we're able to feed them at that rate. These SRAMs can be configured as a level 2 cache, or as a level 3 cache, or as a scratch pad. There are certain times where your workloads are very deterministic, and you do not want to have cache thrashing or other things going on. So if you configure them as a scratch pad, you can pretty much guarantee that the data will be there waiting for you when you're ready, and somebody else, some other processor, will not have thrown it out of the cache. These groups of 32 are interconnected with an on-chip network. We just call it a mesh stop. I'll show you how that's interconnected next. Again, within a shire, you can use some of these new synchronization primitives. We've added to the RISC-V instruction set atomic operations, barrier instructions, credit counters, and inter-processor interrupt support. So here's maybe a good place for you to understand how we've worked in our power saving through operating at different voltages. So you can see these groups of 32 ET minions, they all operate on a single low voltage plane. Even the data caches are built out of special memory cells. We use, instead of a typical 6T cell, a 12T transistor cell. So those can operate down to 300 millivolts. But when you want very dense amounts of memory, the rule in designing VLSI chips is you always want to use the densest cell from your memory vendor. They have optimized that many ways. They do lots of special tricks, and you really want to operate that at pretty much the nominal voltage. And so again, you'll see we have two different voltage domains in this particular unit, and we have many different voltage domains across our chip, and that lets us go in and tweak each voltage domain, particularly for the neighborhoods, the lowest voltage for best energy efficiency, and then you adjust your large DES SRAMs to kind of meet the speed that you need to match that at a voltage that's very close to the nominal voltages. Okay, so now we have to make the shires talk to each other, and that's done over a mesh stop with, I say, large amounts of parallelism. We use lots of wires, and those wires run at the low voltages. And so what you'll find is there are, for example, from one mesh top, say on the left, to a neighbor on its right, there will be several thousand wires in a unidirectional bus going from one mesh top to the other, and several thousand wires coming back the other direction. And this is one of the beauties of using a technology like 7 nanometers. The wires are very small, and you can put many hundreds of thousands of wires for getting high on-chip bandwidth on a chip for interconnectivity. So then let's put everything together here. So we have our shires with groups of 32. You can see kind of in the center here, we have an array of a 6x6 array. We use 34 of those shire positions to put groups of 32 processors. And that's how we end up with our 1088. We needed to use kind of 2 of those groupings at the top right for some other things. We put 4 of our Maxion CPUs in the shire at the upper right, along with a RISC-V service processor. And then we have to have logic for our PCIe bus interface, for DFT fuses, and those are what we call a PCIe shire. On the and this block diagram roughly corresponds to the physical layout on the chip. On the we call the east and the west sides, we have DRAM controllers here. And in order to provide the bandwidth we want, but with very low power, for low power, we use the low voltage swing LPDDR4X DRAM, but we go 256 bits wide. So on the east side, for example, we do 128 bits wide. That's by using 16-bit wide controllers and just using multiple of those that connect upon the chip. Okay, so that gives you then a picture of how the memory is distributed across the chip, how the processors are distributed across the chip, and how they connect to memory. Okay, and so the processors on a chip are all sharing a single global address space. So when a processor, let's say in the lower left, wants to request a piece of data, it'll first ask and see if it's in its local L1 data cache. If it's not there, it goes out to the L2 cache in its memory shire. And that's kind of the L2s are kind of private to the shire. If it's not there, it queries the L3 cache subsystem. The L3 subsystem operates across the entire die. And so that piece of data may be in any shire's L3 cache. If it's in your own shire, you get it a little bit quicker. If not, you make hops out to put the request out, and the shire that has the data on die will send it back to you. And it may seem like it's a lot of hops if your data was in the top right shire and you want to consume it in the lower left shire. But let me tell you, that's still a lot faster than going off chip to off chip DRAM. So overall, it's what you might think of as almost a fairly conventional memory system with L1, L2, L3 caches and main memory. So people who are used to programming supercomputers take a look at this design and go, oh, I understand how to use that. Fairly easy to map problems onto this kind of a structure. And again, while we've done a 6x6 array here, because of this fairly modular design, think of this first chip as the prototype. It's going to be fairly easy for us to scale this down if we want to go to edge devices, or to scale it up in the future to much larger arrays. And at the end of the talk, we'll speculate a little bit on what those larger things might look like in future products without making any actual product announcement. Here's just a little bit more detail to show you that this really is a system on a chip. We have all kinds of other interfaces, UARTs, flash interfaces, GPIOs, timers, interfaces for debuggers, USB. And so this can operate as a standalone chip at times, but quite often in our first customer uses, we'll be talking across the PCIe bus to a host processor. For data center customers, they very much care about security, so we have a root of trust for providing secure boot. And there's a lot of redundancy built in here. Typically, for example, we have enough compute shires here that we can use one as a fully redundant one to control the other shires and have a nice round number of 1,000 for the software to use. So there's a lot of redundancy and opportunities to have fine-grained control over individual positions on the chip, and I'll talk a little bit more about that. We do have full ECC support, both in the DRAM and in the internal memory system as well. So how do we use this in practice? Well, again, if you can get the power per chip down, that means when the customer wants to say, how much performance do you get on a board? We need to compare the performance on a board here, not just an individual chip. So what you can see here is if we think about having 6 chips mounted on the board, our memory system is really a 1,500 bit wide memory system here. We can put up to 192 gigabytes of accelerator memory using 24 DRAM packages, each 64 bits wide. Those 64-bit wide packages actually tend to have 2 32-bit wide DRAMs in a single package here. So you see we can get a lot of memory here to get a lot going. And what you want to do is have a lot of channels. Each one of those 64-bit wide DRAMs is actually made up of 4 16-bit channels. So we end up having 96 of these 16-bit channels able to operate in parallel here. And remember, we have 2 threads per core. So with over 1,000 threads per chip on one board, we get over 12,000 threads of execution going at one time with this memory system. And then those will connect through a PCI switch to the host. So let's take a picture of what look at one of those cards might be like. Here are 6 chips in a mock-up module here that fit on an OCP Glacier Point V2 card, and it can handle, you'll see there are what's called a dual MTOT2 module on the top. It can handle 3 on the top and 3 on the bottom. So this card you see in the background in red is just kind of a standard card, and you could plug, for example, you can turn this into a solid state disk. I believe Facebook has some parts they've work with Qualcomm on that do video decoding, or if you use our chip, you could plug it in and be accelerating AI applications here. And so one card here in that power limit, we believe can provide over 800 teraops when all 6 chips are operating at a gigahertz. So how do you use that card? Well, think of that in our customers this way. So we put 6 chips on a standard PCIe interface card that can drop into what's called the Yosemite V2 sled. And that Yosemite system it's actually a dual x86 CPU system. So it has 2 PCIe slots available as well. So we'd be putting 12 chips in that. You then put 4 of those Yosemite systems in what they call a cubby, right? So now we're up to putting 48 chips in a cubby, and then those go into a rack, and you can hold 8 of these Yosemite cubbies in a rack. So we get 384 chips in a rack, and then some of these large data centers have as many as 20,000 racks in a single hyperscale data center. So our customer opportunity here is to sell millions of chips to just one particular data center, and some of our customers operate many of these large-scale data centers, and of course there's many customers that have this. So that's kind of the business model we had to get started for why we decided to pick going after data centers. There are other places you want to go into as well, and so we do have other form factors. So for example, we can put 1 or several of our chips on standard PCIe Express cards as well. Okay, let's talk just a little bit about software and then the instruction sets here. So most of our customers, we think, will program recommendation models using something like PyTorch. You may use a machine learning framework, and we can get to most of the frameworks here through Onyx models. We started off, our initial software was based on the Glow system that Facebook initially started and then has open sourced. That was nice because it provided for partitioning of models across multiple chips and had a fairly clean separation of the machine dependent versus the machine independent parts. So on the machine dependent part, we went in and were able to change the backend to generate code for our particular CPU. Then we provided our own runtime and our own ET-PCIe driver for the host. And that lets us, again, bring in any of these particular sources, run it through Glow, and run it on our hardware. We're also doing a TVM port that seems to be gaining in popularity. And again, we expect we'll have other software in the future here. So that's kind of a simple view of the software. I know people are kind of curious about what we've done to extend RISC-V. We have added a number of vector and tensor instructions. I'll give some examples in these little blue squares here for different vector ops. We can, not only have computation, but there's conversion. We do scatter gather. Again, for people who are used to programming supercomputers, that's kind of a natural. People understand how to do that. We have transcendental vector operations, not just computation, but also communication. So we can broadcast, do special kinds of loads and stores with interleaves, transposes, reduces, transformations. And again, controlling the memory system is key for keeping high sustain rates. We have some special cache control operations we put in. These barrier credits, atomic operations, particular cache control operations, and how you reserve space in the scratch pad. These were all things we did when we kind of started on RISC-V and said, look, we have to think about this in kind of a supercomputer mentality. We're starting with 1,000 processors on a chip. This is kind of like a lot of data centers that use small number of cores, but they have 1,000 cores in their whole data center here. And so with the Tensor Multiply operations, we can multiply, two-dimensional matrices or three-dimensional matrices here for what we're doing. I won't spend a lot of time on the detail here, but let me just show you an example of how we use these new instructions. So if you think of starting off with our little block diagram here, we have 1,000 cores. One of the first things you might do is a tensor load the L2 scratch pad. And so what this will do is it'll take data that's maybe out in DRAM, or it might possibly be in some of the L3s or a mixture of the two, and it will bring it into a particular shires, into those 4 megabytes of memory, into the amount you've allocated for scratch pad. And those, you can allocate those in different size partitions kind of at will here. Okay. Once it's in that L2 scratch pad, then what you'll do is to do a tensor load instruction. And that will load from the scratch pad memory, the large 4 megabyte capacity, into the individual ET minions, into their local data caches. Once you have the data in the data caches you want to operate on, then you can go and execute the actual floating point multiply accumulate tensor instruction. And so that'll move data into the vector register files and the floating point units directly, and then store the results back in the vector register file. And then we have instructions which do the reverse to get things back out to memory as well. Why so many instructions? Why didn't we just have one instruction and stream all this in like everybody else? Well, programmers have gotten very clever over the last 20 years in figuring out how to overlap the data movement so you can keep high sustainable rates of computation. Again, although everybody quotes peak rates, the goal really is to get high sustainable rates of computation. And so again, there's a wealth of expertise here on how to keep high sustainable rates if you're using a more traditional programming model here. And that's what we've done, and we're very happy with how that works out. So with what we've done, our Tensor FMA operation, we are keeping this near 100% utilization over the 512 cycles that it runs. We can keep the machine, it's how do you keep the beast fed? How do you keep all these ALUs fed on the machine here? So we're able to do that. And again, each tensor instruction in this particular example might do 16,000 floating point operations, all from one RISC-V extended instruction issue here. And again, the RISC-V integer core gets put to sleep during these long tensor operations. So that saves on power overall. The integer, 8-bit integer tensor operations are a little bit different in that we have a separate integer register file that assists the generic vector register file in these operations here, so that we get 4 times the throughput that we get from FP16 when we're doing integer operations. And of course, we do standard tricks like, if you're going to do a multiply, check to make sure if you're multiplying by 0, don't toggle your gates. The answer is going to be 0, just pass the 0 on and go through and do that. We have a number of instructions here for coordination, special barrier instructions, credit counters, and there's again a lot of little programming tricks the programmers can utilize to keep high throughput in the machine here. So let's get to some benchmarks here. So how do we do? So we're trying to figure out a way to give a fair comparison between what we thought we would do, since most of the recommendation work was going on Intel CPUs today. We decided to use the Intel CPU as a reference. And for benchmarkings, we're very much fans of the ML-PERF consortium here, and they have a deep learning recommendation benchmark that they put in. So we're using that. Why? Because as we've learned in benchmarking, it's more fair if you let that vendor cite their own performance on their best configuration rather than you running it and not getting the parameters right. So the performance numbers I'm getting here, let's say for the, on the Xeon 3000 samples per second per die, this comes directly out of going to the ML-PERF website, taking the absolute best performance chip they can utilize and the best system they have with the best amount of memory, and we just use those numbers, right? So you can see that Intel has picked a fairly high performance chip for just 8 chips that are burning 2 kilowatts just for the CPUs alone. So they're operating at roughly 250 watts per die, and they get reasonable performance with that. NVIDIA would say, hey, our GPUs are better, and in fact they are. In terms of relative performance, they're 11 times better in absolute performance. And if you look at the amount of power they're taking there, they don't need 2 kilowatts. They can use just 70 watts per T4 card. And so they're actually 39 times better in energy efficiency, which is shown in the darker green bar chart here. How do different chips compare? You say, oh, the T4 is a little bit old. You say, yeah, but everybody wants to hear about the T4 because they're used to that. The newer chip would be the A10. And so that does a little bit better in absolute performance, about 3 times better, but it doesn't do as much better in terms of energy efficiency, in terms of performance per watt, okay? If you look at what Esperanto can do with this recommendation benchmark, we believe with our 6 chips on a card, we'll get to roughly a factor of 100 times better than those 8 Intel CPUs would do in the system. So we're a great case where the customer can still use the Intel CPU on the host to run the operating system to deal with the I/O, but we're a good partner in terms of being able to accelerate that CPU by another factor of 100. So we're particularly good at deep learning recommendation. Now, at this point in the presentation, if we were sitting in a consortium room, somebody would be raising their hand and say, yeah, but I don't have this number in my performance charts. What do you do on ResNet 50? So, okay, yes, we'll go and we'll give that one next because you all want to compare that. So we do, again, very well, but not 100x better. We're about 25 times better. And that's probably because Intel spent a lot of time making ResNet 50 run well on their advanced CPUs as well. But overall, and here we're able to, we had a Havana-Goya comparison for ResNet 50, whereas we didn't have that for DLRM. And we still do very, very well with a general purpose RISC-V processor as the core of our acceleration here. Okay, it's a little bit on performance. Now let's, oh, I got stuck there a little bit. Just talk about, we have a whole other class of processor here, our Maxion processor here. I'm not going to spend a lot of time on this. It's an out-of-order processor we had designed. Initially, we started off with the Boom processor. We more than doubled its performance. And we have a number of other talks that are out there. Just go look at one of those other talks if you're interested in that, the Maxion processor. Again, we think there will be applications in the future that will want to run standalone. And so the Maxions, it can run, say, I think we have them running at about 1.5 gigahertz now in the lab. They can run a Linux operating system or something else to help drive the array of minions. So just some summary stats here. It's fabbed at TSMC 7 nanometer, about 24 billion devices on a single die. It's only a moderate size die, 570 millimeters squared. We're not going to the full reticle size, which is what, or even wafer scale size, which is what other people are doing. There are different approaches that are appropriate for different usage cases here. Again, 3 different types of processors here. And typically for DLRM, we're expecting to operate these kind of around the 20 watt level or below. The package here has got about 2,500 balls on the back of the package, but there are many more bumps on the die when you chip it over onto the package. We have over 30,000 bumps. What are we doing with all those bumps? Well, in addition to lots of power and ground, one of the things we've done is to realize that with 1,000 processors, there is threshold voltage variation across the die. Or if you get unlucky enough that you have a mass defect, that maybe the processors in the lower left-hand side of the die, they're all running a little bit slow. In order to get to the megahertz you want, you may have to turn up the voltage to get there, but all the rest of the processors, 90%, didn't need so much voltage. So each, you can see in kind of the blue squares here, we have each group of 32. Each of those group of 32 CPUs has its own independent low voltage control. So we can finely tune the power supplies to this. And we think that can offer, tremendous power savings if you get into issues where you have VT variation. Again, as the manufacturing proceeds and matures over time, maybe that's not quite as critical, but we have that flexibility on die. And we can also use those to, again, run different sections of the chip at different frequencies. There are independent PLLs in each of those groupings. So you can run different frequencies, different voltages. You can have the bottom half of the chip running a recommendation half, and maybe the top half running a vision task. Again, there are just 1,000 general purpose processors. Programmers will figure out what clever things they want to do with these. We've got a few suggestions for machine learning, but we expect over time we're going to find all kinds of clever uses for using 1,000 processors. Okay, so where are we at? Well, yes, we have real silicon. Here's a picture of the wafer. We have chips up and running in the lab. We have a remote access for customers for what we're doing here. We're not in general availability quite yet. It takes quite a long time to go through the whole qualification process on chips and get everything finally tuned up. But everything is pretty much running on our very first silicon here. We are still not seeing anything that would require not even a metal mass change on the chip. We're running substantial AI inference workloads on all 1,000+ processors. We're running nightly continuous integration tests on those. The Maxions are up and running. Our PCIe and DDR interfaces are up and running at speed. We have already done a public demo. I think Samsung had what they call a tech day. They were very impressed with what we were doing. And we showed how if you couple a processor with an SSD, that we can dramatically reduce bandwidth requirements in the system. So that's out and that's public. And we're talking to individual large customers at this point, and we have an early access program for those people to get on and start testing our chip. If you're very, very eager, you can contact us now and ask to be in the early access program, or later on this year, hopefully we'll have much more widespread availability. You can get your own PCIe card and play with it. So what's coming up next year? So that's, let me just one slide. There's a lot of interesting things going on. There have been some announcements recently here. So last month, less than a month ago on February 7th, Esperanto announced that we were partnering with Intel to get access to their advanced technology nodes on their fab, to their 3 nanometer and 1.8 nanometer, actually they call it 18A generation. And they also announced in addition that Esperanto was going to be one of their RISC-V ecosystem partners. RISC-V is growing, and Intel has just decided to go big into RISC-V. They've joined the RISC-V consortium, and they announced 4 different ecosystem partners: Esperanto, Andes, and Sci-Fi, who both offer IP if you want to build your own embedded chip, and Ventana Microsystems, who is offering what they call a data class center chip. You'll have to talk to them to see what they're doing. And Esperanto is really focused more on the AI side. With over 1,000 AI optimized RISC-V cores, we by far have the highest performing RISC-V system out there, but that's just the beginning. Today, March 2nd, there was an announcement some of you may not have seen yet, the follow-on to the PCIe bus in some ways. It's called the UCIe bus. The Universal Chiplet Interconnect Express was announced. I think there were about 20 different companies announced so far here. They've announced basically a bus that lets you connect chiplets together. And so if you think of what we've done in 7 nanometer, rather than shrinking to 5, if you shrink directly to 3, what we have is 1,000 processors in a moderate sized chip becomes 1,000 processors in a little tiny chiplet, right? And with little tiny chiplets, you might assemble, you know, let's say 10 of those on a package, maybe with even a Xeon host CPU, who knows, right? And with 1,000 each, you could put 10,000 RISC-V cores in a fairly small package. With chiplet technology here. And so the world is going to advance to where you're not having hundreds or even just 1,000, but tens of thousands of cores able to operate together. How do you program tens of thousands of cores? Well, we believe the general purpose programming model is a really good one, and one that will scale because the world has been scaling data centers and other things to those kinds of numbers of CPUs in the past. So again, I'm not trying to announce any particular product here, but just to say Esperanto very much likes the chiplet methodology, and we like the special packaging technology that Intel has that will help package chiplets. And so you should expect to see very interesting things coming in the future. So I think I've kind of gone over most of the details here. We have this nice scalable design. The stage we're at, we're doing early access for early customers right now. And yes, we are hiring and growing. Go ahead and see our website for details, or send me a personal email if you don't see a slot there that's made for you and you want to do something else. Tell us why you can contribute. Just write that as a note along with your resume. We'd be happy to talk to you. I just want to say quick thanks to a number of our different partners here we've gotten IP from, who've helped us with the layout, with packaging, with input on the design for what they wanted as a large data center customers for debugging hardware, for help, particularly to Semi Dynamics, who's helped us with the architecture and other implementations we got going, to Movelis for the PLLs, Mortic for some of the on-chip sensors. Lots of different customers, and a lot of people have helped. Again, we see different companies in RISC-V not as our competitors, but as members of a common ecosystem. So thanks all to the Sci-Fi and Andes and other companies there who we work together with regularly in the RISC-V consortia out there. Again, if you're interested in some of the details, here are the papers cited in the footnotes, along with a few more details here on how we did the benchmarking. And at this point, if Dennis allows and we can work out the logistics, I'll take a few questions.
I'm blown away. I think you did a great job with this thing. I'm really curious who the other architects were. This is a significant departure from what people have been doing, and I think you've done an exceptional job.
There were a lot of architects here and a lot of people with a lot of industry experience here. We have some of the original people, just a personal thanks to people like Tom Riordan, who helped found MIPS Technologies, Alan Baum, very involved in the instruction set and helping us on RISC-V, various other people, Brian Unowell, Brian Case, Peter Glaskowski, others have been helping. People who've started the SPARC architecture, started the MIPS architecture. We have a number of alpha architects. I think Alan Baum worked on the alpha. Sri Samatala, who's one of the top floating point gurus in the world. He did the floating point on all the VAXes. He did the floating point on the Atanium. He worked for me on my secret project at Intel that I wish I could give you a seminar about, but we never got clearance for that.
Yeah.
And just a variety of different people here. We kind of bit off a very large problem here, and so we used a lot of people with a lot of industry experience who came in at the beginning and helped us out. And just want to say thanks to all of those. There are a lot of fairly well-known names here, and a lot of newer people we're training for the next generation here. We've got I think well over 100 people. Probably 150 to almost 200 people contributed to this design in various ways, kind of directly working with Esperanto.
Okay. If I were giving out gold stars, you got one. Now we can take some questions, and if you raise your hand and so forth, should be able to do it.
Got a question?
Yeah, of course, the other big problem in this space is training. Any estimates on how you do on that, or is this purely inference?
We are certainly capable with the RISC-V instruction set to do some training, and we expect to do some incremental training, but training is a really, really hard problem. And so when we first went to the large data center companies and said, hey, we can build you a really good chip for training, they literally told us, please don't do that. Look, we have over 1 million CPUs in our data center. They have to be ready for handling peak loads. So what that means is most of the time they're 50% idle. We don't care how long it takes to do training. We have plenty of CPU cycles for training. What we don't have is the millisecond level response we need for inference. And so we were really guided into doing more of an inference solution to begin with. Again, I think training needs huge amounts of memory you need to get to. There are just all kinds of very challenging systems issues there. So my hat's off to the companies that are going after training first. We decided to start with inference, and I think we'll grow into training as a company more over time. As I say, we have general purpose RISC-V processors. There's no reason why we can't do some training. The question will be, do we have enough memory for what you want to do for your particular training? If it fits in 200 gigabytes and you can split the work across 6 cores, yeah, that's pretty easy to do. And in fact, if you have a PCIe bus system that takes more than 6 slots, we can kind of add numbers of PCIe cards and get the collective memory up higher. Or if you can just partition your problem in a way, yeah, we could do training that way. But one of the things they said is, look, if you bring us a training chip, it will take well over a year for us to go from buying, a dozen of your CPUs to play with to where we would understand how to deploy this.
And then how about more general high performance computing problems?
Yes, I think the big thing you'll notice that's different at the moment, at least, is the minions don't do double precision floating point. But if your problem fits in single precision or half precision or int 8, go for it. But it's great seeing so many people here. Just to email me, dave@esperanto.ai will get me, and would be happy to be in communication. But thanks everybody for coming. It's been a pleasure to be able to present.
Thank you, Dave. It was really outstanding to have you here. And we look forward to seeing you in person at some point.